I think it's a good time to get started. It's right on time, but it looks like we're full up. So it's my great privilege today to introduce our seminar speaker. Joe Labuz is our current head of department of the Civil, Environmental and Geoengineering. Got that right this time, Joe. I screwed up yesterday. And Joe is an extremely popular head of department. I can attest to the fact that I had to fight off 3 other faculty to have the right to introduce him this morning. So I managed to do that, which is useful. So Joe graduated with his bachelor's degree in civil engineering, I believe, from the I almost said the Indian Institute, but I meant the Illinois Institute of Technology, which is on the south side of Chicago, but Joe tells me not too far south. And then he moved north to Evanston, to Northwestern, where he did his PhD. And then after a short stint as a faculty member at the University of Colorado, he joined our faculty in 1986, I believe, right? Or 1987. We were in the same faculty housing. I remember Joe, when his first kid was born, I was the only person he could find to share a beer with, which has always been a pleasant memory of mine, a fond memory of mine going back. And Joe has made many significant contributions to rock mechanics, to the science and engineering of rock mechanics, very much in keeping with the University of Minnesota and this department in particular, where we have a very long and prestigious contributions over time in that particular area. And he's recognized by the fact that he is a fellow of the American Society of Civil Engineers. And 2 of his most notable contributions, most significant contributions, one would be the development of the plane strain compression apparatus, I did it wrote down here and remember, which allowed people to actually look at cracks in concrete and rocks let them form in a natural setting in a lab, which is a very difficult thing to do, to get something to work in the lab and make it look like it's actually happening in nature. But that's what I believe that the compression apparatus that Joe designed, he has a patent on that, was successful. And the other thing that Joe is really well known for is developing acoustic emission testing. So he was able to actually listen to how damage progressed in rock and concrete. So as we always said, he had spent most of his career listening to rock. So I'm going to hand it over to you, Joe, and you can get to what's going on with this.
Well, first I'd like to extend a warm welcome to our visitors, so thank you for coming to our department and to the seminar. I'd also like to acknowledge the support that we received from Ellis Warren Garden to establish the Warren Seminar Series. With that, the topic for today's discussion is brittle failure of rock and rock-like materials, although the results that I'll be showing you will be from rock and also soil, so dry sand. We're going to spend 20 minutes or so reviewing how these materials respond, how they fail, and then I'll spend the other 20 minutes talking about a general failure criterion, general linear criterion that is relatively unknown. I'd like to acknowledge the co-authors. So Fei Tao Zhang was a visiting PhD student. Professor Li was visiting associate professor, both from China. And Roman Menyenko was a graduate student who is now at the University of Illinois. Other acknowledgments, Jim Meyer was the first graduate student that worked on what I'll be calling Paul-Mohr-Coulomb, this general failure criterion. Justice was an undergraduate student that worked on a fitting algorithm that you'll see in a few minutes. Brian Folta was instrumental in designing and modifying the plane strain apparatus to turn it into a multi-axial device, and I'll explain what that means. And Ali and Jake contributed in terms of experimental results associated with what might be thought as ductile responsive rock, and I'll explain that, and also how rock fails under low mean stress, or rock-like materials. This work started not by Itasca giving us money to look at this general linear criterion, but we had a large project with Itasca in terms of testing, over 100 triaxial tests, and Jim then worked on this failure criteria on the side. Okay, The topic of failure criteria is prevalent in many areas of engineering, and one of the books that I view very highly, both from the theoretical aspect and in fact probably more from the experimental results that are contained in Nadeau's classic book. One of the most important problems in strength of materials is to determine the mechanical conditions which cause solids in engineering structures to deform permanently, and I'll use the term yield, or fracture, and I'll use the term failure. And of course, this can involve both preventing failure. So I have a photograph of our building as it was being constructed. So this is the 7th floor, and you see the vertical hole, that's the shaft. And of course, we want to prevent failure for such a structure, so we need some description of the material in terms of its failure response, or other applications are promoting failure. That is, we want to, in this case, break the rock. Now, this topic is quite mature, and there are several contributions annually on the topic of failure. One review paper contained over 1,000 references on this topic. I won't review the many different types of descriptions, but I want to concentrate on one that's relatively unknown, this general linear criterion. And in 1968, a paper appeared in the International Journal of Solids and Structures titled Generalized Pyramidal Fracture and Yield Criteria by Burt and Paul. So in this paper, Paul suggested a description of failure by this very simple equation. And this should look very familiar to a number of people, because if we take out the middle term, that is, if we let this coefficient b equal to 0, we have the classical Mohr-Coulomb failure criterion that is used every day by geoengineers. The contribution, of course, from Paul was to say that we can indeed include sigma 2, so sigma 1, 2, and 3 Roman numerals, designate the major, intermediate, and minor principal stresses. So he suggested including sigma 2. In addition, we do not have to stop with one plane. We could use multiple planes to describe what appears as nonlinear response of the material. So in fact, in terms of using this plane, it's going to be a piecewise linear approximation of the nonlinear failure surface. So that's what the talk is going to concentrate on. Paul was a very interesting individual. Another major contribution of his appears in the Treatise of Fracture by Labuz. So for those of you that are familiar, Chapter 3 is the mathematical theory of fracture by Rice. Chapter 4 is this contribution from Paul. Other noted contributions, Paul, in fact, wrote papers on rock and appeared at a conference at the University of Minnesota with a contribution. Another seminal piece of work involves the so-called tension cutoff, which was formalized by Paul in '61. And the name of Professor Hodge is familiar, and Paul did indeed write a few papers with Hodge. Okay, so I took a quote from the '68 paper on what we want to do. Because of the wide variety of possible failure surfaces and the analytic complexities associated with many of them, it is logical to explore the simplifications which result if we approximate the general nonlinear failure surface by an approximating surface which consists of a set of planes which hug the curved surface to any degree of accuracy desired. So the degree of accuracy that we're going to work towards is simply 2 planes, as sketched here, but you'll see the richness in the approximation that comes out from using this simple linear relation. Okay, so our objective is to evaluate the coefficients involved with this description of failure and extend this by not only using one plane, but we'll use two planes. I'd like to motivate or describe these coefficients by recalling the classical Mohr-Coulomb failure criterion, which I have written in a very similar form. And the beauty, if I could say, of Mohr-Coulomb are the recognizable material parameters that are very well known to geoengineers. And those material parameters specifically have to do with the so-called friction angle. And the friction angle is typically determined under a state of stress where two principal stresses are equal. The intermediate principal stress is equal to the minor principal stress. And this is a convenient type of loading condition because the way typically a material such as rock is sampled is that we obtain a right circular cylinder, and this cylinder is then encased in some type of membrane, some jacket, such that it's placed in a pressure vessel where two principal stresses are equal to the fluid pressure. And then a force is applied axially to bring about failure of the material. So a common state of stress is where the intermediate stress is equal to the minor principal stress. However, there is also the possibility of using a similar type of configuration, but under the condition where the intermediate stress is equal to the major principal stress. And I'll refer to this state of stress as axisymmetric extension. It's not as common, but indeed we can perform a test where now the radial stress, as I'll call this fluid pressure, is the major and intermediate, and the axial stress is the minor principal stress. And what may come out, of course, it's dependent on the material. I have a representation now on a Mohr diagram where I only have one circle indicated, so half of the circle because of the symmetry of the state of stress is represented on the Mohr diagram. I have one state of stress for compression, another state of stress for extension. Of course, they must meet at the location that I've labeled V sub 0, which has a theoretical meaning of an isotropic tensile strength. So at that particular condition, the three principal stresses are equal and they're tensile. Of course, this is a fictitious point. That is, I cannot perform an experiment to find that value, but certainly geometrically it must appear. And it's possible, depending upon the material, that I would see two different friction angles appearing. And that's the approach now that we're going to take in terms of identifying these material constants with respect to this geometric parameter, V0, as well as friction angles phi-C and phi-E. And the description that comes out, and I'll explain this further in terms of these coefficients, looks like this. So one term is dependent on the on the friction angle in compression, friction angle in extension. If the two are equal, this term goes out, and we have the classical Mohr-Coulomb. Okay, so I'd like to review some aspects associated with any failure theory. And the approach that's usually taken is one that could be described as phenomenological. That is, I'm just going to observe behavior and guess, postulate a certain mathematical expression that applies for that observed behavior. In addition, I'm going to assume that we can use stresses to define the conditions associated with failure. That's typical, but it's not the only approach. The state of stress will be defined by these three principal stresses and their directions. If we are working with an isotropic material, and that's another assumption that we're going to make, Only isotropic materials will be investigated. If that's the case, then the directional dependence disappears, and the only things I need to describe the state of stress are these three principal stresses. In addition, because now I have these only three principal stresses, I don't have to be concerned with the ordering of major, intermediate, and minor with respect to sigma, Roman numeral sigma 1, 2, and 3. I could relax that condition and look at the different combinations that take place if I think about sigma 1, 2, and 3 Arabic numerals. And that will be convenient in looking at a Cartesian coordinate system of sigma 1, 2, and 3 where I don't have this ordering, or I have these 6 different orderings. In addition, I'm going to look at only one failure criterion. That is this one that describes the plane. But the plane will be described in such a way that for the class of materials that we're looking at, one way of describing this behavior is that there's pressure dependence. So as I change pressure, the stress that I need to apply changes. The shear stress changes. Okay, so I've adopted this ordering that I have now 6 relations that describe this plane. So if I look at a Cartesian coordinate system of sigma 1, 2, and 3 without regard to order, I have 6 planes. And if I assume this pressure dependence, these 6 planes form a pyramid, a 6-sided pyramid. The intersection of these 6 planes takes place at the point of V0, and V0 again is the state of stress where the 3 principal stresses are equal and they're tensile, and they do form the vertex of the pyramid. If I also establish another characteristic of this stress space, that is this line that we'll call the hydrostatic axis. Along this line, the 3 principal stresses are equal. So, to represent this 3-dimensional object, the principal stress space is quite nice, but there is another way, of course, that we could represent a state of stress as a point or 6 points, and that is to use a cylindrical coordinate system that I've labeled P, Q, and theta. So the along the hydrostatic axis will be a measure of the hydrostatic stress, the mean stress, and that'll be given the symbol P. If we look at a plane that's perpendicular to the hydrostatic axis, and on that plane, the pressure, the hydrostatic pressure, will be equal. So I can identify a number of these planes that are perpendicular to the hydrostatic axis. Sometimes this plane is referred to as the equipressure plane, or simply the pi plane. And if I do that, then the polar representation of the state of stress involves a distance from the origin to that point, and that distance will be labeled Q, and it is related to the shear stress associated with this particular state of stress. And this angle theta, the load angle, is a way of describing the shape of the state of stress. And what I mean by shape is a representation of these circles that would appear on a Mohr diagram. So now with this apparatus, with the description of either sigma 1, 2, and 3, or P, Q, and theta, let's look at the response of rock-like materials. Oh, a few other things, sorry. So as I said, we can define this failure surface by working with sigma 1, 2, and 3, or P, Q, and theta. Or it may be advantageous because the three-dimensional view may be challenging, to look at a two-dimensional representation, and we'll do that as well. And the planes that we'll be looking at is indeed the pi plane, Q and theta, a section through the failure surface, and that section contains sigma 1 star. So sigma 1 star is the projection of sigma 1 onto the pi plane, as are sigma 2 star and sigma 3 star. So if I look at a section that contains sigma 1 star, which is more or less Q, as well as the hydrostatic, which is more axis, which is more or less P, this section of either this guy or PQ becomes a convenient representation of looking at how the shear stress varies as mean stress changes. Or I could look at a principal stress plane of sigma 1, sigma 2, and you'll see the advantage of that in a moment. So let's look at the pi plane and identify certain states of stress that I've already mentioned that are convenient for us. And that one state of stress is axisymmetric compression. It will be located at these three vertices. And those points are important for us because that's a very simple state of stress in which I could perform a test to determine how the material is failing. The other point to identify is associated with axisymmetric extension, and that's labeled with E. The other nice feature of the pi plane representation is once I have established the behavior within any 60-degree sector, I have the complete representation for that failure surface. Okay, so now let's look at behavior of, I would say, rock-like materials. I'll show results for particular types of rock, but indeed a description of materials that behave in this way are often referred to as rock-like. And perhaps the most telling feature of rock-like materials is the drastic difference in behavior of that material in terms of its maximum load carrying capacity if I pull on the material element or push on the material element. And that's referred to as uniaxial compressive strength in terms of applying a compressive force, or the uniaxial tensile strength in terms of applying a tensile force. So if we think of that cylinder and we apply this force either to produce shortening or lengthening of the element, the response that appears is shown here. And obviously you see a drastic difference in the maximum stress that can be applied in compression, something on the order for this material, 20 MPa, where in tension that value's on the order of 1 MPa. Also, I'm showing here in terms of a diagram of axial stress, axial strain. Axial strain is simply a measure of the change in length of that element. You see a difference that appears whether or not you push on the material or pull on the material, and that's because of the nature of this particular solid. That is, it's a material that contains solids and voids, and those voids can be in the form of pores or cracks, and the presence of cracks gives this different type of behavior. And I like to contrast that with ductile materials where the yield stress does not change whether you compress it or you pull on it. Okay, let's complicate the loading slightly, and that is to include sigma 3. So now I have an axial stress that's being applied, but it's applied in a way where I have sigma 3 present, and typically that sigma 3 would be generated from fluid pressure. So again, I need to have a membrane, I need to have a jacket on my specimen. So this is a failed rock specimen. We're looking at a section, and if you look closely, you could see a polyurethane coating that separates the fluid that's used to generate pressure from entering the rock. So this is, again, stress-strain response for a particular rock, but now at two different values of sigma 3. and sigma 3 remains constant during this loading, and I'm increasing the axial stress. So and I'm also showing axial stress versus volume strain. So certainly there's also very interesting behavior going on in terms of the volume change characteristics. But let's concentrate on the peak value. So obviously as we increase sigma 3, we get an increase in the axial stress that we can apply to this material. If we run a number of tests on the same material and represent the results on a Mohr diagram of normal stress, shear stress, each one of these circles represents a different test, and the envelope that's formed by the tangency, points of tangency associated with these circles is identified with the failure envelope of that material. And obviously you see that this failure envelope is nonlinear. Okay, finally, if we look at this so-called triaxial state of stress, where two principal stresses are equal because it's a very convenient way of performing the test. The results in terms of the description of PQ, so now I have this PQ diagram where I have a number of tests that are being represented, and again, I would say that response, or it appears that the failure surface is nonlinear. The other thing I wanted to point out in terms of so-called brittle failure of rock is indeed there's a peak stress that we can identify that distinguishes this brittle failure mode. In addition, there is eventually a failure plane that's visible, typically at the end of loading. And finally, if we do change the state of stress, and certainly it also depends upon the material, it's possible to see behavior of a rock-like material where there is not a distinct peak, and we continue loading such that deformation continues. And this is sometimes referred to as this ductile response. Okay, a few more items to review, and that is the Paul-Mohr-Coulomb failure criterion, which is well known. One type of popular representation is in terms of the Mohr diagram, because then, of course, we obtain this friction angle. The other parameter that appears that we can identify is the intercept on the shear stress axis, and that's given the symbol little c, and sometimes referred to as cohesion. These are now results where I'm plotting axial stress versus radial stress. And under this representation, it is possible to allow the radial stress to be equal to the major principal stress. The important thing to identify is that a linear representation doesn't do a bad job, fairly good, but at some point I need to cut off my failure surface. And this is this tension cutoff. So if we look closer at this tension cutoff, what we would need to do to modify our failure criterion, our failure surface, is to simply recognize that for rock-like materials, this very simple description of the minor principal stress being equal to the tensile strength, no matter what the other two stress components are, provides a good description of failure. And that's shown by these points that lie along this horizontal line. So by using this type of geometry where we take advantage of the difference in cross-sectional area, we can produce tension in the axial direction and generate at different radial stresses different values of the mean stress to investigate this tension cutoff. And it appears on a Mohr diagram as this particular part of the failure surface, and in the Cartesian coordinate representation, it appears like that. Okay, so now let's talk about PMC. So as I said, Paul introduced this very simple description of failure, and he did include the intermediate principal stress. And in his 68 paper, he identified the material coefficients by looking at simple states of stress. That is uniaxial compression, so sigma 2 and sigma 3 are 0. And it's fairly easy to show that A would be given by 1 over C0, where C0 is the uniaxial compressive strength of the material. From this representation on a Mohr diagram, we can identify the parameter C0 by looking at this triangle that's formed from V0, the center of the circle associated with uniaxial compression, and the friction angle in compression. And we get this term. I can do the same thing for sigma 3. That is uniaxial tension. I would have sigma 1 and sigma 2 equal to 0. And I can show that C is equal to this term. And then for B, the state of stress is associated with isotropic tension. And we get this term. So now this is the failure criterion that we call Paul-Mohr-Coulomb, and we want to apply this to various types of rock. Okay, so we're going to perform experiments on isotropic material, and we want to look at brittle failure. So the states of stress, of course, are important to us in terms of seeing this type of peak response that appears. Different stress states that we'll be looking at: axisymmetric compression, intermediate is equal to minor. Axisymmetric extension, the intermediate is equal to the major. And then we'll be looking also at multi-axial compression, where the principal stresses are not equal. They take on different values. For completeness, I've identified what P, Q, and theta are in terms of these principal stresses. So in terms of actually performing the test, we measure principal stresses and we can compute these quantities. So we want to apply Paul-Mohr-Coulomb using one plane fitting, and then I'll explain two plane fitting and the richness that appears just from those two planes. Okay, it's convenient in terms of this fitting process to rewrite PMC in terms of PQ theta. I won't go through the transformation. If we look at PQ, the representation of the failure surface for compression extension are shown here, and for other states of stress are shown by multi-axial. The straight line, of course, intersects the Q axis, and we'll designate those parameters BC, BE, and B theta for compression extension and multi-axial loading. We're looking on the pi plane, and the representation of K is in terms of this value of alpha, which is basically the measure of the shear stress at the condition where the mean stress is 0. Okay, so now we have this equation that allows us to do this fitting conveniently, and let's look at some data. So these two results, this is now data that is generated by running this type of test where I either have a state of stress of axisymmetric compression or extension. So for convenience, I'm plotting the extension data on the negative Q axis. So you see the data fits fairly well with a straight line, both for this type of rock, a Berea sandstone, as well as this type of rock, again, another sandstone, but red Willmore. These are the results now, both for the Berea and the red Willmore, as well as some other types of rock. And the parameters that we should look at are the friction angles in compression and extension. And for all these materials, there is what might be called an intermediate stress effect. That is, the friction angle in extension is larger, certainly for the sandstones. For the limestones, not that much larger than the friction angle in compression. Okay, we can also apply this failure criterion to a material such as sand, dry sand. It's convenient to look at the representation of the data now in a diagram of sigma 1, the major principal stress, and sigma 2, the intermediate. For conditions where sigma 3 remains the same value, and the results then are associated with a value of sigma 1 and sigma 2. So all these points, these tests were conducted at the same value of sigma 3, in this case this 207 kPa. And the representation on this diagram for PMC will be a straight line with the slope of this value, where NC and NE and NC are related to the friction angles in compression and extension. And you see, again, a fairly good fit to the data, so PMC works very well for dry sand, these particular sands. Okay, so now let's go to two planes. With two planes, we have 6 material parameters, and we'll identify those parameters simply as ABC with superscript I. The way we'll describe, again, these coefficients is in terms of friction angles in compression and extension, as well as this V0. Now, it's interesting, and we'll show, that there are 4 possible pyramids that develop. And the failure surface itself, in terms of following this representation, will be given by the smaller q. And what I mean by that is shown in this pi plane description. So we have 2 planes that we find from fitting of the data. And again, the value of q is represented by a line in this view. So you see, if I look from the origin to this line associated with axisymmetric compression, I hit this plane before I hit this plane. So the failure surface is defined by this plane. In addition, if I look in the direction of axisymmetric compression, I hit this plane before I get to that plane. So that will then define the failure surface. So let's look at the 4 possibilities. And they are a 12-sided pyramid, a 6 to 12 to 6-sided pyramid, a 6-12-sided pyramid, and then this special case of a 6 that stays 6. So let's look first at the ones that won't appear from experimental data. They're interesting to look at, but special conditions must happen. And the first is this 12-sided. So for a 12-sided pyramid to appear, both vertices must be at the same place. So V0 for both planes must be equal. If that happens, these 2 pyramids combine to form this 6-sided, where if I look at the PQ representation, what I would see is no change in slope. And that's not typical behavior of a rock-like material. In addition, the other thing that is a characteristic of this 12-sided pyramid is I will see no change in shape on the pi plane. And again, that's not realistic. That does not appear for rock-like material, although it's an interesting geometry. The other one that's also fascinating is this 6 to 6. And now we'll be looking at a diagram of a section through the pyramid. And this is this sigma 1 star square root 3 times p. So this is the hydrostatic axis. This is q. These are the 2 planes, plane 1 and 2. So plane 1 will be blue, plane 2 will be red. And again, the smaller q dictates the shape of the surface. So this distance represents the shear stress q. I hit the red before I hit the blue, so that governs failure. this surface is developed in such a way that the intersection on the compression side and on the extension side take place at the same mean stress. And if that happens, then I can have this pyramid that starts out, of course, as 6, and then it changes to 6 with no transition. So it's a very special case where these guys are equal. And the description then on the pi plane is quite fascinating. That is, these lines are parallel, even though the even though the friction angles for those two surfaces are different. But because of the two different V0s, we have this representation. Okay, so those are artificial, those are interesting to look at, but now let's look at failure surfaces that are observed from our data. So again, I didn't say this, we use the representation in terms of these planes. That V01, that is the vertex associated with plane 1, will be larger in the absolute value sense than V02. So this is a failure surface now where I have 6-sided, it's governed by red. Then I have 12-sided, that's governed, if you want to think about it, on the compression side by the blue, on the extension side on the red, and this is the 12-sided region. And then eventually it comes back to 6. And this is the representation of that figure in the Cartesian space of sigma 1, 2, and 3. So I have 6. Then you see this region where I have red and blue, that's the 12, and eventually I get to a mean stress where I have the 6 again. And the representation on a opaque representation is shown there. So again, the red is the 6, I have blue and red, that's 12, and then beyond that point is just blue, it's 6-sided. And on the pi plane, it looks something like this. And the nice feature of this type of description is that I do have a change in the failure surface on the pi plane. So depending on the value of the mean stress, the shape changes. Okay, and finally, the representation of the 612. Again, I have two different V0s, but now I have an intersection at only one point, either on the compression side or on the extension side. Typically, in terms of data of Rocklike material, it will be on the compression side. So it starts out as 6, and then it converts to 12, and it stays 12. The shape does change, so the opaque version is shown here. So the red is the 6, then I have red and blue, that's 12, and it stays 12. And again, you see this change in shape on the pi plane depending upon the mean stress. Okay, so now we have the machinery. Let's look at data. And a convenient way in terms of this 2D representation of looking at the data, again, is to go to this diagram of major principal stress versus intermediate stress. And each color is associated with a particular value of the minor principal stress. So you see these planes appearing in terms of the fitting for one plane versus the other plane. So this two-plane fitting. This is for a particular rock. In this case, it's a trachyte, an igneous rock. In this case, it's a siltstone, a metamorphic rock. This particular rock has the characteristic of a type 2 failure surface, that is the 6-12-6, and this rock is 6-12. This is the results now for those two rocks as well as others. You see the 6 parameters associated with these friction angles and extension and compression. And again, we can apply this to sand, so this is just contrasting sandstone versus a particular sand, and I'm just showing the representation now on 3D space of sigma 1, 2, and 3, and the data points as they appear in stress space. Okay, that's it. Oh, item, and that is now what could we do with this? Well, of course, we have now this failure surface that we could define with one plane, two planes, or more that include the intermediate principal stress. We have recognizable material parameters. Are there other things that we can do? And the answer is yes. And one of them is if I only have compression data. So now we're looking at data from this one data set for Dunville sandstone, where these tests are conducted under axisymmetric compression. So this is the only data I have. I can assume, as what's done in Mohr-Coulomb, that the friction angle in compression is equal to the friction angle in extension and perform the fitting. So that's 4 parameters, not 6, because the friction angles are equal in compression and extension. And you see the fitting for one plane and the other plane. The representation on a Mohr diagram is shown here. So we have plane 2, the red plane. I've also included the tension cutoff that we should use for a rock-like material. We have the other plane, and the transition between these two planes is shown by this broken circle. And this circle represents a number of stress states, because remember, the circle can involve sigma 1, where sigma 2 is equal to sigma 1, or sigma 3, and sigma 2 is equal to sigma 3. So this failure surface turns out to be a type 2, where I have 6, 12, 6. And the comparison in terms of the 4-parameter fitting with the 6-parameter fitting is shown there. Okay, now I'll end. This general linear criterion is we call it Paul-Mohr-Coulomb in honor of Bert and Paul for suggesting this type of approach. We showed that it is convenient to use this type of representation to model the behavior of rock-like material. And if we have multi-axial data, that is, if we can fit 2 planes, indeed it can do a good job just with 2 planes and 6 material parameters. That's it. Thank you.
So let's have some questions, but if you can just put up your hand, and I need to bring you the microphone before you can ask the questions. So we have some questions from someone. Stefano, just wait, be patient.
So it seems that one ingredient behind the complexity of this problem is the difference in behavior of the material between compression and tension, right? It's one of the characteristics of these materials that plays a role. Because you mentioned it as
I agree. So I don't know where you're going with that
so
comment.
obviously that's a premise. If that is true, that this complexity in failure mechanism is somewhat associated with this dichotomy of behavior between compression and tension.
So again, I agree.
Yeah.
And I guess I can go further, and I alluded to it, that certainly these types of materials are ones where I have solids as well as voids, and the presence of those voids be, if they're pore-like or crack-like, certainly influences the behavior that we see. And it's clear under the simple state of uniaxial loading, compression or tension, that both in terms of strength and stiffness, it appears.
Right.
Now, in terms of going to what I call brittle failure, if you're asking me if this type of behavior that we see is because of the makeup of the material, I would agree.
Because the part of the question would be if it would be interesting or feasible within the experimental platform that you have to try to map out the failure mechanisms of other systems that have other material systems that have a distinct behavior between compression and tension. For example, like our soft architected materials that might be dominated by buckling mechanisms in compression and might not have them in tension. If it is, for example, an interesting parallel problem to investigate from a failure standpoint.
It could be. I guess the other thing that I did point out, and I didn't say much about it, but certainly it's very important. And the other comment I need to make is that when I'm talking about this brittle failure, the overall state of stress is one of compression. So even though we describe this axisymmetric extension, the mean stress is compressive, and it can be quite high. Now, a very important characteristic of these materials is the volume change behavior, so dilatancy. And certainly dilatancy is also very much affected by mean stress. So that the material behavior, and I should have pointed this out in terms of volume change characteristics, lower mean stress, this material is quite dilatant. Even though I'm applying compressive state of stress, at some point the volume increases. So I have an increase in volume. And this changes depending on mean stress. So that's where I think the interesting behavior is coming.
Okay, Manuel wants to ask a question.
So thank you for the very nice lecture. You have really described a phenomenological model, and I'm wondering if you could speculate, or if you have speculated about micromechanical reasons that are behind the observation that you have. For example, the fact that you have two types of friction angle and so forth. Is there anything that one can say, from a micromechanical point of view?
Yeah, so as I said, the approach that, and it's typical for describing failure, is one of just observation. Certainly there has been considerable effort in looking at some type of micromechanical model. A fracture appears within the solid, and depending upon the state of stress, conditions for describing this crack growth, can we then explain the overall response that appears? I guess to answer your question, I haven't given thought to why, from this micromechanical point of view, we would see a difference in compression and extension friction angle. So I can't provide an explanation.
So, Joe, I have a question. You're going to answer my question? Yeah.
Maybe. Tired.
So, okay, I could see you were. So you identified a number of different failure mechanisms, and you associated some with artificial materials, right? You said that these are artificial in the sense that you wouldn't observe them in the process, right? When you identified these different failure surfaces, if I understood it correctly. And you said these are kind of artificial, they're interesting to look at, but they're artificial. And my question is, could you actually, if you could create a material that would follow that failure mechanism, what advantages might that material have? Or would it have any, is it possible to make a material that would follow those mechanisms that you identified?
If I said failure mechanism, I misspoke.
Okay,
so
well, maybe I misinterpreted it. Yeah.
I didn't mean to imply that those surfaces are associated with different failure mechanisms.
Failure surfaces,
I would say the failure mechanism is the same. It's this fracture that forms. I did have on one of the bullets, and I forgot to mention, more or less, deformation is uniform up till peak. So, okay, there's probably a small crack somewhere near peak, but more or less that shape remains a cylinder or remains a rectangular prism. And at the end, we see a fracture. So those type 1, type 2, type 4 failure surfaces have nothing to do with the failure mechanism. It's the same. Okay. It's the behavior that we observe. And I said it's artificial because, for one, in the fitting, you're never going to get the V0s to be the same. In addition, that one doesn't capture what I observe. So there should be some decrease in strength means
so
stress
my question
increases.
is, could you construct something artificially that would do that, right? I mean, like people have constructed materials that have negative Poisson coefficients, for example, right?
Yeah,
So-
I don't know how you would do that.
Okay.
I mean, and the other one is just interesting geometrically because it shocked us when we saw that on the pi plane, the failure surface is parallel. But that's because of the two different V0s and how it links up. The next step is to create these surfaces in 3D printing. So we have the 6 plane with the cutoff.
Oh.
We have to do the 12 plane, 6, 12, 6.
Okay, any more questions? So let's thank Joe one more time. And then for the